Good evening, everyone. I hope you're all doing great. Welcome to the AI webinar hosted by E2E Networks. I am Tanya, your host, and today we are diving into a crucial topic in the world of artificial intelligence. How a neuro-symbolic approach fixes GenAI reliability issues. We are thrilled to have with us an expert in this field, Joshua Thomas, co-founder and CTO of CogniSwitch. Thank you, Joshua, for joining us today. Before we start, let me give you an introduction to what we do at E2E Networks. E2E Networks Limited is the leading AI first hyperscaler from India, focusing on providing advanced cloud GPU infrastructure. We lead the industry as a prominent cloud GPU provider, offering comprehensive range of NVIDIA GPUs, including HGX H100, A100, L40S, A40, V100, and T4s. We are also excited to announce that E2E is bringing the NVIDIA H200 GPU to India for the first time. This is set to supercharge our AI capabilities, and we are proud to lead the way. The H200 advanced architecture enhance performance and dramatically accelerate your AI workloads, enabling you to tackle more ambitious projects and delivering results faster than ever before. Let me introduce our speaker for today. Joshua Thomas, co-founder and CTO of CogniSwitch, a visionary with over a decade of expertise in AI and computational linguistics. As the former CPO of Icon Labs, Joshua has been at forefront of cutting-edge innovation, now challenging his passion into building CogniSwitch, a new age knowledge fabric designed to supercharge the capability of LLMs. Joshua's work is rooted in applying machine learning and deep learning to unlock insights from diverse types, including natural language, image, audio, and video. His earlier ventures include iEngage.ai, a platform that empowered human machine collaboration to tackle challenges faced by community, whether a city, a company, or even a country. With the track record of driving AI-driven solution to solve real-world problem, Joshua continued to shape the future of intelligent system. Be sure to check out CogniSwitch.ai for a glimpse into how his latest venture is transforming the landscape of AI. Now, over to you, Joshua.
Hey, thanks, Tanya. Hey guys, thanks for this opportunity to run through what we're doing at CogniSwitch and Neuro-Symbolic AI, and some of our learnings about how they can help in fixing reliability issues as well in generative AI. So let me pull up the screen, and I will quickly walk through a presentation. Post that, we can have a question and answer as well. Is the screen visible?
Yes.
All right. So there's this term that's been going around today. It's caught up from an academic thing to something that is out in corporates and institutions trying this out. It's called Neuro-Symbolic AI. People have always been wondering what this is, so we find out what it is soon enough. Let me first get into challenges today that we have with generative AI. Next slide. Yes. So quickly, three high-level challenges that generative AI has are data issues, quality control issues, and compute overhead costs. I'll go through each one of them. When I say data issues, I mean the two types of data issues. One is that the model itself could be trained with unclean data, could be representative of a bias. We see that there are some generations that are weird and quirky, or possibly racist. there's so many issues. Some people get abused by support chatbots. For some reason, there are some linkages. Someone found the Pokemon Magikarp. Uh, it is continuously repeating in a loop, and all of this kind of points back to an issue with the way that the model was trained. And so that's one aspect of this. It's at the very beginning, which is the training biases, I would say, of data. The other part of this is now that you do have the model, what is it that we store and retrieve? And on the right side, for example, here's an example of how people use generative AI. Supposing it's a large language model, what they're doing is they're considering comparing a query embedding to the embedding of a chunk. And that's not going to cut it at all, because we already know that one, there could be a training issue. And then now you combine that with the fact that these models actually learn a dense embedding space, which means that each and every concept, each and every thing that it is seen in the data is very close to each other. So there's a chance that it can get activated if you, for example, say something about a totally random concept, let's say a computer. And for some reason, that computer was used for analyzing something about, let's say, monkeys, right? And so this could activate. And the reason why this happens, and this happens in the real world, is because people are storing and retrieving chunks to start with, which are like dense and packed with concepts, and then they're trying expecting it to retrieve it back when you have a query, which is a much smaller sized string, and expecting the matches to be relevant. So one is data issues, and we'll get into hallucinations and all of that as well. The second part is the larger point of the quality of responses, right? How do you control for quality? Um, this is a new technology. People are still trying to figure this out. Um, and one of the biggest issues with this is how do I ensure that my response is sticking to the point, right? And this is a major concern. For example, I already mentioned offensive or abusive or hateful content generation. It is also important when you expect the response to adhere to a certain standard. So it could be that a company has a policy about what kind of data can be generated, what kind of content, or whether it is text, or whether it is your audio or video, what kind of data can be spoken about in the generation, right? Should you have any frills attached, right? And so it becomes important to ensure that your generation is compliant. The next point is about traceability. So a lot of times, relating back to even the training data, you don't know, what has been used in, whether you've run a reinforcement learning loop, or whether someone has misused your data and generated a deep fake, for example. And so it becomes important uh, to be able to say, hey, this is where I got this data from, right? And the biggest thing is when you do finally give that response, uh, you don't usually have a neural model saying, "Hey, I told you this. I gave you this paragraph, or I generated this way because of XYZ reasons." Right? They don't list down uh, what happened. It's a black box, right? And so explainability, interpretability is very important. So a last fleeting point, there's a large movement towards training models, sometimes smaller models, sometimes the large models on private machines, uh, sometimes retraining it, not just using the weights of it. And that is an expensive operation, even if it is a smaller model. Uh, and of course, not just that, when you're doing a fine tuning or an inferencing, you still run the cost of having at scale, like, 10,000s of inferences, for example, uh, running a large overhead in terms of compute, in terms of storage, memory, and compute itself, right? So, what is neuro-symbolic AI? People know about this, and this is probably like a refresher. The more recent, uh, you know, heavyweight in AI has been the neural models, and just maybe a few decades back, symbolic AI was the the kind of hero of AI, and so we basically these are two different approaches, and I'm gonna equate this to perhaps what we say about our left hemisphere and our right hemisphere. And so a symbolic system is something that is explicit, that thinks and reasons slowly about each step, and then reaches an inference, right? It can either deduce why something happened, or it can infer what is going to happen. It is, in some sense, you would say it is that conscious thinking, as opposed to uh, this neural side of things, which is a little bit subconscious. It's more instinctive. This is not with symbols necessarily. People call this sub-symbolic, but this is more implicit. And Daniel Kahneman, in his book Thinking Fast and Slow, talks about how we interact with the world as well. And we tend to think either uh, reflexively, like the equivalent of a neural network, which he calls System 1. And sometimes we think slow. So even before that reflex to react comes in, we might say, hey, let me just reason about this, and let me think about this. And he calls this System 2. So we believe that these two things should come together. And one other thing that CogniSwitch advocates is uh, the importance and the primacy of a logical reasoning unit, kind of an interface between these two aspects. And these are getting more and more blurred, the lines. Uh, but in whatever we're trying out, we realize that this needs to be called out. That you do need some amount of logic and reasoning, and you need a system that is given that responsibility as well to manage these two aspects. All right, so moving on, do we need both? So there's a lot of people saying that Gen AI is it. We're at AGI, and people are saying you don't need anything else. Uh, you can probably all your reasoning can happen through that. But in our experience, what we've realized is that that's not completely true, and we've realized that that's what's causing all of those generation issues as well. So quickly, some thoughts on kind of the trade-offs between the two. So back in the expert system symbolic age, we had a difficulty in encapsulating all the rules, right? All the concepts, and we found it difficult to, think slowly about each and every little nitty-gritty. Uh, Whereas, thanks to the scale of today's models, it's actually allowing us a compression of that work, and it's allowing us to automate that, and in fact generate uh, graphs and knowledge systems concepts, right? The other aspect is that on the flip side, you'll see that the neural network just learn something totally random, like I mentioned in the training, right? So this random association, you don't know why, uh, maybe uh, the smell of coffee makes you want to write, right? And you don't know why. And it's exactly like that. This is something that is implicit, and this leads to hallucination. On the flip side, you don't have that problem in symbolic. You don't have a precision problem. If something is brought, retrieved, it is brought for a reason, and it's very clear why that is happening. Um, and again, on the symbolic side, we have recall issues uh, because of perhaps in one text you had a reference to a financial institution, and in another text you had a reference to a bank, and uh, this could be like totally different symbols and was never equated together. A neural approach can help with some of that, like at least narrowing down the search space to the most likely neighborhood, and then we can, you know, bring these two concepts, bring these two approaches together, um, and allow it to work for us. So, so yeah, I mean, you need it. You need both. So at a high level, how does this look? Like a, you know, 10,000 feet view would be, you have some input data, which is usually some unstructured content. This runs through that system, the neuro-symbolic system, which would have neural representations of the symbols, rules and logic, and neural representation of the rules and logic itself, and um, allow this to, for example, give us symbols to put back into our knowledge system, which you would also use for content generation on the LLM side. And finally, you might also want to run a validation loop back to the same system and get a final response. So let's delve a little bit deeper into this, right? Uh, so at the bottom, what you're seeing is um, the various contexts of, how people might use it, and let me just run through some of that. So at the leftmost is basically what we call a provisioning stage. So there could be all sorts of content like text and audio and video, images. Um, this needs to be understood. This needs to be mined for what we call concepts, and this needs to be stored in a reliable way. In order to do this mining is where we think these large models, whether it's language, vision, speech, audio, um, that's where they shine. They've seen so many patterns, and you're not asking it to generate, you know, something novel. You're asking it to understand, almost like the extractive AI that we had previously, right? Now it's generative, but this is applied to an extractive task. This with certain constraints in the form of ontologies, where we say that you cannot, have a property associated with a bank that looks like, let's say, mitochondria, and it's, a biological concept, right? Uh, it could also mean that you have to necessarily have a location for a bank. It also involves in this layer where we're doing the transformation and we're trying to mine knowledge out of this. It involves knowing what type of content this is, what kind of source this is, and kind of juicing this out uh, for the most information. So it's kind of like transforming data into knowledge, right? And so that's the transformation that you see in between. And then this is stored, for example, in CogniSwitch. We use a mixture of a vector and a graph data structure. We try and keep this hybrid and control this with rules and logic, a reasoning decision engine, and this is managed by us, and this is stored in the equivalent for vector being the neural type of data, and the graph being the symbolic type of data. So coming back to the bottom, uh, the pipeline remains similar. It changes according to context a little bit, but you finally go and retrieve things once this provisioning, which is the leftmost part, is over. You start to retrieve things. So you might be looking for certain concepts and certain uh, um, even the sources of the context sources of those concepts. You might ask the natural language query, for example, And you will again have to mine this to understand this. You will again have to apply constraints. You will have to transform it in a way that we can retrieve the relevant data from the vector and the graph data structures, applying the business rules and logic, and you get a certain relevant set of reasoned data points. So we call this a reasoning chain. This is not in itself a final response for GenAI applications. So this is then given in a generation request. So the last two that you're seeing on the right side are what we call guardrails, and some people give us the generation request. So they ask us to, take this data and safely and reliably give a generated response, which again goes to the same process of seeing, okay, what are those compliance norms of the business that needs to be adhered to? Am I leaking information? Is this private information? Ensuring that all of that is in place and then generating a reliable response. Or the rightmost, some people generate it based on the data that we give them on their own, but they want a validation. Hey, did we generate the right thing? And so they come back to us, and we again are a validation, and we are able to say, hey, you generated this, but we can tell you why you generated this. What are the data points that support this generation? Are there any totally random like non-facts in your generation, for example? And this is how we manage these four types of operations in a neuro-symbolic way. So takeaways. Um, we basically realize that these large-scale neural models have the best utility in understanding unstructured content. Like I mentioned, both neural and symbolic approaches will be required at the moment. Um, and the biggest takeaway is at this point where we are right now, the biggest factor here is managing your data and ensuring your knowledge is also well managed. How do you transform the data? How do you keep that data? How do you ensure that you have what is representing your business's rules, your business's concepts, entities, and interrelationships between those entities? That is of paramount importance. And the benefits quickly, it's a kind of a reference to the challenges. You now have data that can be audited, so you know where this data came from. Why is it that certain concepts are present in your knowledge system? You are able to adhere to your governance, risk, compliance norms. So if a company does not want to generate certain types of content, you can validate and guardrail that. You have, of course, the large language models and uh, like OpenAI, Anthropic, all these providers, they have safety filters themselves, but you have an additional layer of a safety filter as well. Apart from that, the biggest thing here is you can literally see it's not a black box anymore. You know where this data has come from. It's not come from someone misusing your data. It's not come from the model's own parameters. It's come from your knowledge source. And what we realized is this has actually reduced a lot of cost in terms of token consumption. We'll get into that shortly. So a view into mitigating hallucination. So we previously saw the slide where we were talking about how people are vectorizing chunks and comparing chunks to small strings of queries. A deterministic approach in this case, where we're using the large language model not to retrieve, but to actually provision in the starting phase. So now you have a deterministic approach uh, where you can like reliably and in a way that is explainable get out data points and then generate on top of that as well. So that's the left and right that you're seeing out here. So your risks are handled better. And it's all in any engineering discipline, it's all about risk. It's all about handling. It's not that you cannot have a bug in your code. It's the fact that you actually have a reliable, understandable way of handling certain possible risks. And we realize that we can keep like a lot of cost low after the initial provisioning stage when you're doing the retrieval. There's a lot of costs that are slashed. We also realize that some amount of latency, like waiting for the model to come back, and even the fact that you needed to have large infrastructure to manage all of these inferences, all of that comes down as well. And yeah, this is another view into that, where we realized uh, this is like there's a lot of tokens being used, not just in terms of vectors, but in terms of the fact that the LLMs are used um, in actually reasoning and um, coming to some reasoned conclusion, trying to use the neural approach to be more symbolic. But that doesn't work. And we've seen that it keeps failing. You need that symbolic structure, and you need something more deterministic. Byproduct, you have a lot of slash tokens, and you have a great cost benefit as well. Yeah, so finally, there's still ongoing research happening, um, uh, both in academia and in the industry, and there's kind of a convergence that's happened now that since the 50s, and people started branching out into neural and symbolic and um, ML and DL, and it's all starting to come back. Um, and I think that even with the recent OpenAI releases and um, even others like Google's release, and we are seeing that people are trying to figure this out in kind of like in one model. So like it is both neural and symbolic, and trying to influence both the neural and symbolism uh, inside of that model with reinforcement learning. A lot of the algorithms that we use in constraint satisfaction programming, graphs, and reinforcement learning, that's there are a lot of you know overlaps and similarities, and people are starting to use similar algorithms as well. And people haven't given up on uh, looking beyond the transformer. So that's kind of the next steps uh, with regards to research and development in all of this. Um, and we in CogniSwitch, we're looking at this as um, a long shot of ensuring that any enterprise can have their digital twin of knowledge, not of anything else. We're not saying like have a MySQL database, or we're not saying um, have maybe like a docx stored, um, or an Excel on a OneDrive, right? We're saying your primary asset is your knowledge. You need to capture this from your people, from your documents, from your conversations, and that becomes your primary asset. And in order to create this digital twin of enterprise knowledge, we realized that we needed to have a more reliable way of provisioning and retrieving this. So we're on this journey of figuring this out, of making this happen, and these were just some learnings that we came across as well. Yeah. So thank you. If there's any questions, I can take them now.
We are now open the floor for questions from our audience.
No questions?
Let's just wait for another 2-3 minutes. I think there is one question. Yes. What does the new structure looks like when you use an LLM to extract, and what exactly are we extracting here?
Yeah. So what we are extracting is, so when I say concept, for example, right, let me talk about a leave policy. So in a leave policy, you have various types of leave policies. Say you have vacation, you have casual leave, you have paternal leave, maternal leave, right? You don't want to be taking the chunks. You want to be taking, you want to be mining what it is talking about. So the way this looks in our system, if we had to visualize this, is you can think of um, leave as the overarching concept, which has subtypes, which are casual, sick, maternal, etc. And then under that, you have various clauses. You have uh, various concepts like, hey, have you been working for a year? Then you're eligible for, so and so type of leave, right? So what we are extracting is an understanding in that sense. What we used to do manually in the symbolic day, um, what we used to do was actually manually put this data in. We used to sit with experts, understand, um, for example, in a manufacturing plant, understand when the boiler goes off, when the boiler is at critical temperature, what are the potential scenarios. So this all used to be extracted in that sense, but in conversations with experts, and then we used to encode that into systems, and that was a symbolic AI summer, and then the winter happened when people realized it couldn't be scaled, and this was like at 1990 that winter happened, and then recently we've had explosion of neural approaches, and then we realized that even after scaling them, even though for tasks and stuff like that, it can even be a zero shot SOTA, it is still not able to be employed reliably. So, and that's where people are looking at combining these two, a neural and a symbolic approach.
Yeah. Because of the link issue, some people joined late. So they are requesting if you can show your slides quickly one by one, just for 2 minutes. That will be really helpful.
Let me know if it's coming up.
Yes, it is visible.
Oh,
This
so
is the last one.
I
I
need to go back. Yeah, hold on. So the first part was about the challenges. There were, challenges with uh, training, challenges with storing and retrieving it. So it's a lot to do with data. Um, the second part is with regards to quality control in terms of compliance to certain business standards and norms, tracing where this data came from, interpreting why this response has come. Uh, Third challenge is about costs of maintenance and uh, whether it's an inferencing, fine tuning, and people are also trying to train models from scratch. So those were some of the challenges I covered. Um, so this is basically going through each challenge a little bit more expanded. And yeah, then we come to Neuro-Symbolic AI itself, where I'm talking about these two types of thinking, these two types of how we try to solve the problem, and we realize that on its own, they're not enough. And you need like even a logical reasoning unit as well to interface between these two types. Um, and pros and cons of, symbolic and neural, um, difficulty in capturing all of that expertise, random noise in neural approaches, recall issues in symbolic AI, where you have like a different reference entirely to the same concept. Um, so this is a high level view. This is again a little bit more deeper, where we're talking about four contexts. We're talking about provisioning context, a retrieval context, and a generation and a validation context. So um, the neural models are used. Uh, One aspect of this is, a neural model, as in like the large language model being a neural model. The other aspect is inside of uh, post the symbols. We also try and use this in a graph neural network and predict on the basis of that as well. So you have, for the provisioning stage, where it's generative, right? That's what I was focusing on. You have all these language, vision, audio models being used. You constrain that. So generally, we do find uh, that if you don't constrain that in the provisioning via ontologies and a certain structure, then even in this provisioning stage, you can have hallucinations. And so we try and constrain this as much as possible. Uh, we also have the option, like in CogniSwitch, we have the option of a human in the loop, so that there can be a quick curation on some of this. We also know when uh, the generation is low confidence, etc. So some of these can kind of handle that risk. Uh, but in our experiments, usually the constraining is pretty helpful. You don't even need to fine tune a model then. Yeah, so the takeaways are, you primarily use this to understand um, whatever your content, whether it's language or images, video, better. You do require both approaches, and if you try and formulate the problem as a data or a knowledge problem, data and a knowledge problem, that becomes much more useful, because people miss the point sometimes. They think that the data is ready, and it's not. It's not ready to be utilized by AI. And people also miss the point that there's like tons of facts of concepts interrelated with each other, just sitting in the minds of people, sitting in conversations, sitting in emails, sitting in documents. All of this can be mobilized to become a source of knowledge itself. But it's not in its raw form that it's knowledge. I mean, when we read it, it is. But for a machine to understand that, you need to transform this, which is what we saw in the previous slide. That that transformation has to take place, and then you can manage your knowledge. So, and we call this a knowledge system. Like this whole thing, we call this a knowledge system, which uses a neuro-symbolic approach. And the benefits here are, then now you know what has happened to your data. Uh, if you're going to be reusing this, you know how it is going to be reused. That's even in the response generation, you can interpret, you can explain why, what concepts have intersected, what is brought together this final response. Uh, you also stick to the point. You don't create like random responses unless you want to have a creative response, then that's fine. And you also, people have used this for validation purposes, like they had a certain standard of response generation to be adhered to, and so ensuring that that response is adhering to that standard. So it's kind of a compliance issue. People are also used in compliance in the sense of uh, they want to validate uh, some compliance document and some data and ensure that the data is in compliance. So these are governance risk and compliance issues that use cases that we've seen as well. So yeah, this is again pointing out the risks on the left side, and then uh, on the right side how we're handling those risks as well. Uh, Again, a view into cost, latencies, uh, again, costs, and further research. So that's kind of it.
Yeah, there's one more question. It's a follow-up question from the first one. Can the LLM hallucinate when extracting these concepts?
Yeah, that's what I refer to, right? So it is a possibility that the LLM can hallucinate, but in our experiments and when we were working with live data, we realized that having an ontology, it actually constrains it way more than just asking it to just randomly, mine concepts out of it. So having the structure of saying that here is an employee has employee ID, accounts, um, it has certain department, having that structure in place, right? So we realize that that actually makes it's kind of an anchoring. So interestingly, even humans, right, in Daniel Kahneman's book, like we also anchor, we also attend to certain data points in our mind. And similar to that, like we realize that even these models are doing that anchoring. Um, there could be like really, some small percentage of point percentage of uh, this happening. Uh, but like I said, all engineering disciplines, Microsoft shut down like 1 out of 5 computers. So it's not impossible for anything to go wrong, right? If that's what we're looking for. Uh, the idea is how do you have fallbacks, guardrails? How do you ensure safety in the event that things go wrong? So that's the idea.
Yeah, one more question. Regarding the architecture diagram, in that top block, there's rules and logic along with the vector base and graph database. How this rule and logic is built is stored in graph database. Is the rules and logic is used for search and retrieval from graph database?
Yeah. So like we have the option of connecting to whatever database you want to use, but what we do is we keep this together. So because again, costs, maintenance, duplication, right? So keeping this together gives us some benefits. I'm talking about the vector and graph data structure, and thereby the algorithm that you run on this also, you have faster reads, and you have certain benefits as well. Uh, the rules and logic is partly contained in the ontology, uh, partly contained in. So we realize that the concepts itself sometimes are to be used back again. That's why I kept it in one block. It has to be used again inside uh, a use case as a rule and a logic. So it's a little meta, but uh, it's actually generation of the rule and logic from a human from a natural language description of the rule and logic. And there is one part of this which is the business rules and logic, and then there is the data rules and logic, which is at the I put that at the lower part, which is at the transformation level. So it is in the graph structure as well as an execution layer for us. So it is both. And at the execution during search and retrieval, you would be like ensuring that constraint is uh, happening according to that rule and logic. Either not to show some data or mandating that this field is required when you're showing this data.
Yeah, I think that is all. Okay.
That's it.
That concludes our webinar for today. A big thank you to Joshua Thomas for sharing his expertise and to all of you for joining us today. For more information on E2E Network's AI solution and upcoming events, please visit our website. Have a great day. Thank you, Joshua. Thank you for joining us.
Thanks, Tanya. Thanks everyone for joining.
Thank you,
Thanks.
everyone. Bye.
Yeah. See you. Bye.